Hello and welcome to another slide video in the advanced course series from the Cornish Radio Amateur Club, and today we're going to have a look at feeders. So let's have a look at feeder basics, the syllabus item for the RSGB Advanced Certificate. 5A1 says that we need to understand that the velocity factor of a feeder is the ratio of the velocity of the radio waves in the feeder to that in free space, and that the velocity factor is always less than unity. We also need to calculate physical feeder lengths given the frequency and velocity factor, and we need to recall that the velocity factor for coaxial feeder with a polythene dielectric is approximately 0.67 or 2/3. We need to recall that feeder loss increases with frequency and that lower loss feeders may be desirable at VHF, UHF and above. So we also need to look at 5A2, understand that a quarter wave length of feeder can be used as an impedance transformer, and apply simple examples of the formula Z0 squared equals Z in times Z out. And that's one of the formulae that you will be provided with in the exam on the formula sheet. And we need to recall the basic construction and use of waveguides. So let's get started. Feeders are transmission lines for radio. Now when we talk about transmission lines, there's a whole gambit of theory that goes with that, and transmission lines can take many different forms, not just the coax or open wire feeder that we are used to. On the top left there you can see a section of waveguide showing the flanges where you bolt two pieces of waveguide together. Top center, fiber optic. Fiber optic lines are also transmission lines. Perhaps more familiar, on the top right, a length of feeder with a PL259 at one end. At bottom left, less familiar or less thought about as a transmission line perhaps, big long high voltage transmission lines used by power companies. Bottom centre, open wire feeders used on a large HF commercial site. And bottom right, some microline filters made out of, they're printed onto a board, but they utilise transmission line theory for their operation. So, when do we think of a wire as just a wire, or when do we think of it as a transmission line? Certainly, if we're looking at normal circuits with short lengths of track or short wires, we can say that in many electrical circuits, the length of the wires connecting the components can be generally ignored. The voltage on the wire at a given time can be assumed to be the same at all points. So when we measure one end of a track on a PCB and the other end with an oscilloscope, we shouldn't see any phase difference between the two, because the length of track at the frequency that we're measuring shouldn't cause a difference in phase. But if we look at long reels of transmission line, for example, or long lengths of transmission line, for example, a reel of coax, we can say that, however, when the voltage changes in a time interval comparable to the time it takes for the signal to travel down the wire, the length becomes important and the wire must be treated as a transmission line. Now this is when transmission line theory really comes into its own, and we can no longer assume that if we measure the voltage at one point on the line at an instant in time, that further up the line the voltage will be the same. So there's a rule of thumb that, and it's a very approximate rule of thumb, that if the length is greater than a tenth of the wavelength, the phase delay and the interference of any reflections on the line become important if the length is greater than a tenth of the wavelength. And this can lead to unpredictable behaviour in systems which have not been carefully designed using transmission line theory. This is not to overstate it, and this is not to say that every time we use a long line we need to delve into mathematics, but we need to be aware that the nature of the line changes from being just a wire to a transmission line. So let's have a little look at the history. Now, you don't need to know this for the exam, but to give some background, if we look at the four on the left, Faraday, Gauss, Ampere and Kelvin, these are the guys that developed independent theories around electricity and magnetism. And it was Maxwell that pulled these together and came up with what we now know as Maxwell's equations. In fact, he came up with a whole range of equations, perhaps 20, of which 12 were particularly significant. And it fell to Oliver Heaviside to condense these Maxwell's work, if you like, into 4 equations which are very well known and often used in transmission line theory. So the equations, which were, as I said, reduced to 4 by Heaviside, Gauss's law, where charges produce an electric field. Gauss's law for magnetism. He said there are no magnetic monopoles. There's no such thing as a magnet with simply a plus, a north pole, and no south pole. Faraday's law that time-varying magnetic fields produce an electric field. And Ampere's law that steady currents and time-varying electric fields produce a magnetic field. And the latter part of that was due to a correction by Maxwell. So these are the 4 equations. We don't need to have any knowledge at all of these for the exam. Again, it's just background. But you can even buy a T-shirt with them on. They're considered to be so essential, if you like, to the deep understanding of electromagnetic waves and how they behave, that people have put them on a T-shirt. Anyway, moving on now to what is in the syllabus. Restating that feeders are transmission lines, and there are 2 common types that we will deal with. One is the open wire feeder, sometimes called the ladder line, where you've got 2 conductors and spacers holding the conductors a fixed distance apart. And this is a balanced feeder. And then there's the coax cable, which has a center core and a braid spaced from the center core by a dielectric. The dielectric trying to behave as much like air as possible. And we call that an unbalanced feeder. Now let's have a look at the characteristics of these 2 types. Well, both of them have a resistance of the conductors, R, and any resistance from end to end of this transmission line, be it the open wire feeder or the coaxial feeder, will cause losses. But because the lengths we use are fairly short and the cable's fairly thick, we tend to ignore this in our calculations. But if there is any resistance in a feeder, it will cause any currents flowing down the feeder to generate heat, and this will manifest itself as feeder losses. The individual conductors have inductance. Any long length of wire has inductance, manifesting itself as self-inductance. And so that is one of the factors that we do take into consideration, the inductance of the conductors. And capacitance between the conductors. Again, if you have 2 long pieces of metal, albeit that they're wire, spaced apart, there will be capacitance between the conductors, and indeed in the unbalanced coax between the central conductor and the braid. There will also be capacitance between the conductors and earth, and that will depend on the siting of the coax. So there we have it. L and C are the main characteristics, and we tend to ignore R. But as we say, R does contribute to the loss. So this equation, this formula isn't in the exam sheets, but in the sheet given to you in the exam, but it may be important to remember it because it is in the book. So whether it comes up in questions or not, I'm unclear. But it just says that the characteristic impedance of a feeder or a transmission line is equal to the root of the inductance over the capacitance. Z0 equals root L over C. So, reminding ourselves that feeders are transmission lines, what will affect the characteristic impedance? Well, what affects it for the open wire feeder or the ladder feeder, the balanced feeder there, is the wire diameter and the separation between the wires. They will affect L and C, and then hence Z0. And for the coaxial feeder, it's the diameter of the inner and outer conductors. So when we look at a feeder length, we assume that for it to have its characteristic impedance, it has to be of infinite length. In other words, any smaller length will be terminated in the another piece, which will also have a termination value of Z0. So every chunk of the feeder, if you like, every finite element of the feeder will be terminated in a similar finite element, so that looking in we will see Z0. But as I say, this is only if we consider them to be of infinite length. Another way that we will achieve Z0, or the characteristic impedance, is if we have a shorter length of feeder and we terminate that shorter length in the characteristic impedance itself. And then we will see Z0 looking into the feeder. So for the upper example there, the ladder line, if it was 600 ohm ladder line, then the top resistor terminating the ladder line would be 600 ohms. And then, irrespective of length of the ladder line, we would see 600 ohms looking in to the end of the ladder line. Similarly, if the bottom feeder was 75 ohms television coax, and that was terminated in 75 ohm resistor, then looking into that coax for a shorter length we would see 75 ohms. If the termination wasn't 75 ohms, if it was some other value, then we would see a mismatch and we would not see Z0, or the characteristic impedance, looking into the feeder. The longer the feeder, the more closely we would see Z0, but we wouldn't actually see Z0 unless the feeder was either of infinite length or terminated in the characteristic impedance itself. Let's look at the signals on the feeder lines. The balanced feeder relies on the fact that on each conductor the signal applied is of equal magnitude and opposite direction at any instant in time. And that's shown there on the screen as two signals in antiphase, but of equal amplitude. The fields generated by these equal and opposite signals cancel out, which means that all of the energy is contained within the feeder itself. On an unbalanced line, the entire signal is applied to the center conductor, and the entire energy is contained within the inner surface of the braid, the outer conductor. This makes a coax cable very useful because we can feed it through walls with ease, and we won't be disturbing the signal because it's all contained within the inner surface of the braid or outer conductor. This is not the case with ladder line. If we disrupt the fields on the ladder line, then the cancelling effect is destroyed and the ladder line won't work properly. So returning to the coax cable, the full signal is on the inner conductor and the return current on the inside of the outer conductor or the braid. Now there are circumstances when we need to connect an unbalanced system to a balanced system, and for that we use a Balun, and this has been mentioned I think in both the foundation and intermediate courses. This is an example of a Balun. On the left we've got a transformer coil with a balanced signal applied, and you can see the signals there in antiphase and of the same amplitude. And on the right we have a coax connected across a secondary to that transformer, and the centre of it is connected to the one end of the transformer, and the braid is connected to the other. And as the braid is connected to the bottom of the transformer and the braid is at earth potential, we can connect that to earth. And note that the centre tap of the primary, where the balance is connected, is also connected to earth. So you'll have the balance system on the left swinging around plus and minus of a centre tap earth potential, and on the right you will have the unbalanced feeder with an earthed braid. So this is a balanced to unbalanced transformer, and in this one, because there are the same number of turns on the primary and the secondary as depicted in the picture, we haven't tried to do any impedance transformation. We've simply tried to match balanced to unbalanced, and this is a common way of doing it with a Balun. So we remember that a transmission line always has two conductors, and a balanced line relies on the equal and opposite signal on the conductors, whereas an unbalanced line, the coax, contains a field inside of the braid. So this is a transformer Balun. There are other types of Balun that don't use transformers, and we'll be looking at those later on. But this, because it uses a transformer, is a transformer Balun. And this is bidirectional, as are most Baluns, in as much as you can transmit either on the balanced line or on the unbalanced line, similarly receive on the balanced line or the unbalanced line. If a Balun is not used, the coax braid may radiate or pick up signals. So we simply connected a balanced line, the two terminals or two conductors of a balanced line to the centre and braid, we would find that instead of the braid just returning being the return path, it itself would have a signal on it, and this causes problems both in the transmit and the receive direction for us. In the transmit direction, it means that the field is no longer contained within the coax and therefore can cause interference to other devices. And this plays into the EMC chapter of the book Advance. In the receive direction, it means that household devices, perhaps near our system, might radiate into the coax and therefore get into the receiver. So it can cause us interference from other devices because the braid is no longer containing the signal completely within the coax. So if we look at the transformer Balun, there we've said that because the turns are the same on the primary and the secondary, we're not seeking to provide an impedance match. But as commonly found, coax can be of 50 or 75 ohms, and typically open wire feeder is manufactured to have impedances of perhaps 300 or 600 ohm. So if we connect a balanced feeder to an unbalanced feeder, or a balanced system to an unbalanced system, we need to perform two tasks. One is to match the Balun balanced to the unbalanced, which we've just covered, and the other thing is to match the differing impedances. So we use the transformer, and instead of having the same number of turns on the primary and secondary, we can use it as an impedance transformer. And the formula you see there says that the impedance of the primary is equal to the impedance of the secondary times the primary turns divided by the secondary terms squared. So this allows us then to make an impedance transformer. Now that formula has three terms, a little bit like V equals IR, with V being analogous in this case to ZP, I being analogous to ZS, and NP over NS squared being analogous to R. And so we can use the same technique that we've used in the past with the formula triangle to change the subject of the formula. So using the formula triangle, we write the form of the formula that you're given in the formula sheet in the exam, ZP equals ZS times NP over NS squared. But if we wanted to have ZS as the subject of the formula, we can simply rearrange it using the triangle by covering up ZS and saying ZS equals ZP divided by NP over NS squared. And you might find this useful. Less usefully, you could also make NP over NS squared the subject of the formula. But in order to solve for one of those turns ratios, I think it would require algebra that is not expected at the advanced course. So let's have a look at some Baluns then. Here's a 1-to-1 Balun. It has 6 turns on the primary and 6 turns on the secondary. The primary, as shown before, is connected to earth at the bottom end of the winding, and that's connected to the braid of the coax. And the centre conductor is connected to the top of the primary. The braid is earthed, as is the centre of the secondary, and the balance feeder is connected to the top and bottom of the secondary. And just a reminder there with the antiphase but equal in amplitude signals on the balance system. So we call that a 1-to-1 Balun because there's been no attempt to do any impedance transformation. Let's have a look at this one. Slightly different configuration, but a 4-to-1 Balun. Now this could equally be drawn with separate primary and secondary, although it could have been drawn, it could just use a single coil to achieve the same result. And you can see it's got 6 turns to 12 turns. And you might say, well, that looks like a 2-to-1 or a 1-to-2 Balun. But the 4-to-1 ratio there doesn't refer to the number of turns, it refers to the impedance. So if we look at the term that sets the impedance there, the transformation, you remember from the formula on the previous slide, the term that is significant is NP over NS squared. And if we have a look at that, in our case it would be 12 over 6 squared, which is 2 squared, which is 4. So that's why it's a 4-to-1 Balun. So transformer baluns are not the only types of baluns that are used. Here we have a sleeve balun. On the right hand side is a normal piece of coax with the braid connected to one arm of a dipole, perhaps a half-wave dipole, and the centre conductor connected to another arm. A wider diameter braid, perhaps harvested from a piece of coax of slightly greater diameter, is cut and sliced and spliced over, slid over the original coax. And this is soldered at the point shown by the yellow dot to the inner braid. So we've got the outer braid and the inner braid, and they're soldered at this point, joined together. It's important that this is a lambda by 4 or quarter wavelength length of outer braid, and this means that the sleeve balun is only suitable for a single frequency, or extending the point a little bit, perhaps a single band with acceptable performance. So if you picked lambda by 4 to be mid-band, then you could use this type of balun over the entire band. Lambda by 4 is quite long at some of the HF frequencies, so this is probably more useful at the VHF and UHF and above. So the large diameter braid is soldered to the coax's braid, and the dipole arms are soldered to the inner coax braid, and the outer braid is insulated over its length, apart from where it's soldered, the rest of its length from the inner braid, and that's quite important. So reiterating for this one that the sleeve balun is only really any good for a single frequency band. For wider bandwidth, we can use a choke balun. Here we have on the right a piece of coax. Again, the outer braid, or the braid rather, is connected to one arm of a dipole and the center to another. And slid over the coax are ferrite rings, so toroids, and these increase the inductive reactance of the braid. So the ferrites should cause a reactance, which, in other words, the 2 pi FL, large enough to attenuate or choke off the currents in the braid. Remember, it's if the braid is carrying any signal currents where we get our problems. Now you can use this technique as well if you feel that you've got some sort of mismatch occurring somewhere, even if you're using baluns externally to the shack or something like that, you can always use this technique to further attenuate any signal current in the braid and therefore improve the performance of the system. If you do get some mismatches, you get standing waves formed. Here on the picture we have an incident wave. Incident wave is the wave travelling towards the antenna, which in this diagram we've called a mismatched load. And the reflected wave is the wave that comes back from the mismatch. So for example, if the feeder were 50 ohms and the load was 200, at that mismatch point a reflection would occur and the reflected wave would travel back. And as this travels back, it reinforces the incident wave, and we end up with a standing wave formed on the coax. And that standing wave is the vector sum at any particular point of the incident wave and the reflected wave, and therefore greater in amplitude than either. So there we are, the incident wave and the reflected wave joining to form the standing wave. Now the worst types of mismatch would be either an open circuit feeder or a short circuit feeder. And let's see how a short circuit appears at various points on a feeder. Remember that we are now looking at transmission lines, and so we acknowledge the fact that the voltage isn't the same at any point when we measure along the feeder. So there's a feeder, and here is the physical short circuit applied. Now at the short circuit point, the voltage has to be 0. This is similar to working with wires. If you have a short circuit and you put an AVO across it, of course you won't measure a voltage across a short circuit. So there we've shown with the curve above labelled V that the voltage there is 0 at the right hand side. V must be 0 at the point of short circuit. Similarly, at a short circuit you'd expect the I of the current to be a maximum, and indeed that's what we see. The maximum current flows at the short circuit point. And the trick with these is to start at the point of match or mismatch and work back towards the source. So if we draw back the voltage and current distribution back towards the source in terms of wavelength, we'll see V in antiphase, in this case, to I. And if we look at the various points there, at the input to this particular feeder, the impedance, Z, equals V over I, and in this case it equals infinity, or at least it's going to be very, very high, because I equals naught. So whatever V is, anything over naught is infinity. If you put it in your calculator, depending on the model of calculator, it'll either say inf or error or something like that. You can't sensibly divide anything by naught. And in fact, some of the losses in the feeder will stop it being infinity, but it will be certainly a very high value. A quarter of a wavelength further up towards the load, Z equals V over I again, but this time V is 0. And so at that point, a quarter of a wavelength further up, we are measuring an impedance of 0. So what we can say is that the impedance at various points back from the load changes from short circuit to open circuit every quarter wavelength. So there we're showing a short circuit with Z equals naught, and a little bit further up, a quarter of a wavelength further up, we're showing an open circuit at lambda by 2. So a partial mismatch causes a standing wave. So we've said a full mismatch there causes a standing wave, but a partial mismatch also causes a standing wave. And here we have a feeder with characteristic impedance 50 ohms, terminated with a 33 ohm load. And this is causing the same sort of picture as with an absolute short circuit, but we're not getting voltages going down to 0, because if you measure the voltage across the 33 ohm load, it won't be 0 as it was with a short circuit, but it'll have a finite value. And here we see the values that would be present as you go back in lengths of a quarter of a wavelength back from the mismatch. So in this example, the feeder will alternate between 33 and 75 ohm impedance as you go back. We can use this effect to our advantage. If we reduce the length of a feeder to just a quarter of a wavelength, then, for example, put in connect a 50 ohm antenna to it, we can use this to do impedance transformation. So here the problem posed in the book Advance is to match two Yagis, each of 50 ohm nominal impedance, to a single 50 ohm transmission line or feeder. Now you might do this if you stacked or bayed two Yagis to increase the gain of the station. So if you had two Yagis, each of 50 ohms, and you wanted to match that to a 50 ohm, you would use this formula here. This formula is given in the sheet that you'll be given in the exam. And it says Z0 squared equals Z in times Z out, or the characteristic impedance squared is equal to the input impedance times the output impedance. Now this formula relates to a quarter wavelength, and it's important to remember this. This isn't a general formula for any length. This relates to quarter wavelength transmission lines. So once again, this is three terms, and we can use the triangle to change the subject of the formula, or we can use some algebra. Either way, we'll end up with Z in equals Z out squared, Z in equals Z naught squared over Z out. So let's have a look. If we use 75 ohm coax here, then looking into this system with a line line characteristic impedance of 75 ohms and a load of 50 ohms, that's Z out, then we would have an impedance of 112 ohms. So using a quarter wavelength of transmission line, or coax, connected to our Yagi antenna, we've transformed the impedance to 112 ohms. So there we are, 112 ohms, looking into the quarter wavelength of 75 ohm characteristic impedance coax and the Yagi. And if we do the same with the second Yagi, we've got two 112 ohm loads there, or impedances. And if we put those in parallel, we will have a combined impedance of half, or 56 ohms. And we can match that to our 50 ohm line. It isn't an exact match, but it's close enough. And this is the example given in the RSGB book Advance. So, also noted in the book is that if you have two situations where you have short circuit feeder and an open circuit feeder, then for the open circuit feeder it will appear to be alternately capacitive and inductive every quarter wavelength, and for the short circuit feeder inductive and capacitive every quarter wavelength. I'm not sure how this will manifest itself in questions, but we'll figure that out as we go through some examples in class. It may be something you just simply have to remember by some method. Let's look at SWR and return loss. We looked in a previous slide at the incident wave combining with the reflected wave and producing a standing wave. This is because the reflected wave is reflected at the point of mismatch. So in other words, the characteristic impedance of the feeder is not the same as the impedance of the load. And the formula you're given in the book is SWR equals Vmax over Vmin. That's the maximum voltage that appears over the minimum voltage. Or you can say the addition of the forward and the reverse voltages, because remember the waves combine, over the subtraction of the forward and reverse voltages. Again, they're combined but being subtractive at this point, and that gives you Vmin. So those are the two formulae you can use to calculate the SWR if you're given the voltages. Now, in the book Exam Secrets, there was an example where instead of being given the voltages, you were essentially given power. Now, power relates to voltage P equals V squared over R. So if you're given the power, you've got two choices here. One is you can take the square root of the voltages and work it out from that, or you can use this formula, which isn't, I don't think, given to you in the sheet, but is the correct formula to use if you have power. So the only option there is to memorize this one and have it in your head as you go into the exam. So if you're given, for example, 10 watts forward and 1 watt back, then PF would be 10 watts, and PR would be 1. And you plug that into the calculator, and hey presto, that will give you the SWR if you're given power. The upper formula gives you the SWR if you're given voltage. One of the items mentioned in the syllabus was the velocity factor. Now we know the velocity of electromagnetic radiation in space or air is about 3 times 10 to the 8th meters per second. We use that in the V equals F lambda formula. Now the velocity of the signal in the transmission line divided by the velocity of the signal in free space is a velocity factor. Electromagnetic waves will travel at a maximum speed that they will travel, the speed of light, 3 times 10 to the 8th meters per second in a vacuum or in air. In any other substance or medium, it'll be slower. And the ratio of the velocity in the other substance, perhaps a open wire feeder or something like that, to the velocity in space, that is the velocity factor. So you need to remember this for the exam, and that is that a solid polythene coax, the velocity factor is 2/3. In the book Advanced, there are some other examples, for example, open wire feeder, I think, has a velocity factor about 0.8, 0.95 or something. But the one that they seem to require you to memorize is that in solid polythene coax, the velocity factor is 2/3. And any questions will be formulated around this. Now, this value isn't given in the sheet that you're provided, so once again, you will have to memorize that. Velocity factor is 2/3, or they quote it as 0.67, approximately the same. So, let's do an example. What's the length of a half wavelength of polythene coax at 145 megahertz? Well, the first thing to do is to work out the wavelength of 145 megahertz. And using the formula V equals F lambda, you can use the triangle to change that to lambda equals V over F. And because we're looking at free space, that would be 3 times 10 to the 8th over 145 times 10 to the 6th. In other words, 145 megahertz. And that evaluates to be 2.069 meters. Well, the question asks for a half a wavelength. So we simply divide that in half, and we get 1.0345 meters. But what is it in the polythene coax? Well, we multiply that 1.0345 times 2/3. In other words, the velocity factor. So you can either multiply by 2 and divide by 3 on your calculator, or you can multiply it by 0.66666 or 0.67, it doesn't matter. The multiple choices won't be close enough to cause confusion there. And the answer comes out to be 69 centimeters. Now, this is the example from the book Advanced, and it differs slightly from the answer, differs slightly because I use 2/3, which is fine. If you use 0.67, you will get exactly the answer that is in the book Advanced, but these are not material differences, and you will be able to select the right choice from the multiple choice offered. So once again, remember that the velocity factor in solid polythene coax is 2/3. Finally, let's have a look at Waveguide. There's a pictorial representation of a piece of waveguide, and this is WG17, and its dimensions are 18 millimeters times 9.5 millimeters, and it's useful for frequencies from 10 to 15 gigahertz. This is the example also given in Advanced. Now, Waveguide operates in a number of modes, and we don't need to know anything about the operation of Waveguide. The only fact that we do need to remember is that the lowest cutoff frequency is where just a half a wavelength will fit in the major dimension, in other words, the 18 millimeter. So normally it doesn't run at that sort of a frequency, it's run at a slightly greater frequency, so it'll comfortably operate. So inside the waveguide, if it's steel, it will be plated in some way with copper or something like that. It must have the lowest resistivity possible, since the currents that flow on the inside faces of the waveguide are the main loss mechanism. And the whole idea of using waveguide is to, instead of coax, is to reduce the loss, because coax starts to get lossy as frequencies go up. Now, where would you use coax and where would you use main waveguide? Well, the general rule of thumb is below 2 gigahertz. Top quality coax is better and less lossy, and so you probably would select that. Above 8 gigahertz, waveguide is definitely superior, and coax becomes quite problematic. And between the two, The choice depends on the application. A short length on a circuit board might well be fine with a piece of high quality coax. Longer lengths might require you to use Waveguide. So that pretty well sums up the chapter on feeders. Actually, the chapter is on feeders and antennas, but antennas are going to be covered in a separate video. Thank you very much for listening.